For most of human history, space was something distant, a place to observe, to imagine, but not a place to visit. Even after the first rockets were built, space travel remained limited, rare, difficult, accessible only to trained astronauts. Yet in recent years, something has begun to change. A new phase of space activity is emerging, one that involves not only governments, but also private companies. Among these companies is Blue Origin. Its goal is not only to reach space, but to make access to space more common, more routine, more sustainable. One of the ideas associated with this shift is the concept of space tourism, the possibility that ordinary people, not just astronauts, could travel beyond Earth. At first, this idea seemed unlikely. Space travel was too expensive, too complex, too risky. But with advances in technology, costs have begun to decrease. Launch systems have become more reliable. Reusable rockets have changed how missions are planned. This has opened the door to new possibilities. Suborbital flights are one example. These flights reach the edge of space, allowing passengers to experience weightlessness and view Earth from above. The experience is brief, but it represents a significant change. It shows that space is no longer limited to a small group of individuals. Beyond short flights, there is a broader vision. Space hotels, structures placed in orbit, designed to host visitors for extended periods. These concepts are still in development, but they are being taken seriously. Designs include rotating habitats that could simulate gravity, living spaces adapted to microgravity environments, systems that provide air, water, and energy in a closed loop. The idea of living in space, even temporarily, introduces new challenges. Human bodies are adapted to Earth's gravity. In space, muscles weaken, bones lose density, fluids shift within the body. These effects must be managed carefully, but they are not insurmountable. Research supported by NASA continues to study how humans adapt to space environments. This knowledge helps inform the design of future habitats. Private companies, including Blue Origin, are exploring how to create environments that are both functional and comfortable. The goal is not only to reach space, but to stay there, to make it part of human activity, not just exploration, but presence. The idea of space hotels may still feel distant, but it reflects a broader shift. Space is becoming more accessible, more integrated into long-term planning. What was once extraordinary is slowly becoming possible. The rise of private space companies marks a significant change in how space exploration is approached. For many years, space activity was dominated by government agencies. Organizations like NASA led missions, developed technology, and defined the direction of exploration. This model achieved remarkable success, but it also had limitations. Missions were expensive, infrequent, focused on specific goals. The involvement of private companies introduces a different dynamic, one that emphasizes iteration, efficiency, and scalability. Companies such as SpaceX and Blue Origin are developing technologies that aim to reduce costs and increase the frequency of launches. Reusable rockets are a key part of this shift. Instead of building a rocket for a single mission, parts of the system can be recovered and used again. This changes the economics of space travel. It makes it more sustainable, more repeatable, more accessible. Private companies also bring different approaches to design and development. They test, they refine, they iterate, often at a faster pace than traditional programs. This does not replace government agencies. It complements them. Public and private efforts work together. Agencies provide long-term vision and scientific goals. Companies provide innovation and flexibility. This collaboration expands what is possible. It allows for more missions, more experiments, more opportunities to explore. The private space industry is still evolving. Its long-term impact is not fully known, but it is already clear that it is changing how space is approached. From rare missions to continuous activity, from isolated projects to growing infrastructure. And as this shift continues, space becomes not only a destination, but a domain of ongoing human activity. For a long time, rockets followed a simple pattern. They launched once, they completed their mission, and then they were lost, burned in the atmosphere, falling into the ocean, discarded after a single use. This approach made spaceflight extremely expensive. Each mission required a new vehicle, a new set of components, a new investment of time and resources. It was effective, but not efficient. The idea of reusability changes this completely. Instead of treating rockets as disposable machines, they can be designed to return, to land, to be used again. At first, this idea seemed difficult to achieve. A rocket returning from space is not like an airplane coming in for a landing. It is moving at extremely high speeds. It must control its descent precisely. It must slow down at exactly the right moment, and it must land upright. All of this happens in an environment that is constantly changing. Atmospheric conditions vary. Fuel must be carefully managed. Guidance systems must respond in real time. Despite these challenges, companies like SpaceX have demonstrated that reusable rockets are possible. Through repeated testing and refinement, they developed systems that can return to Earth and land vertically. At first, each landing was a significant event, a demonstration of control and precision. Over time, as the number of successful landings increased, the process became more routine. This shift has important consequences. Reusability reduces cost. It increases launch frequency. It allows for more missions, and it makes spaceflight more accessible. It also changes how space systems are designed. Instead of focusing on single-use performance, engineers consider durability, maintenance, turnaround time. These factors become part of the system. Organizations like NASA work alongside private companies, integrating reusable technologies into broader mission planning. The result is a more flexible and responsive approach to space exploration. Reusable rockets are not just a technical achievement, they represent a change in perspective, a move toward treating spaceflight as a system, something that can be repeated, scaled, so expanded. And as this approach continues to develop, it opens the door to more ambitious goals. While rockets are currently the primary method of reaching space, there are ideas that explore entirely different approaches. One of the most well-known is the concept of a space elevator. At its core, the idea is simple. Instead of launching from the ground with a rocket, a structure would extend from Earth into space. Along this structure, vehicles could travel upward, carrying cargo and possibly passengers, without the need for traditional launches. The concept relies on a cable or tether anchored to Earth and extending far beyond geostationary orbit. At that altitude, the outward force from Earth's rotation balances gravity. This creates a stable point from which the structure can extend both downward and upward. The main challenge is material strength. The cable would need to support its own weight over tens of thousands of kilometers. It would also need to withstand environmental stresses, wind, temperature variations, impacts from debris. Currently, no known material can fully meet these requirements. However, research into advanced materials continues. Some theoretical materials, such as carbon nanotubes, have properties that could make such a structure possible in the future. Even if a full space elevator is not built, the concept influences thinking about space access. It encourages exploration of alternative methods, more efficient, less energy intensive, more continuous. Instead of discrete launches, access to space could become a steady flow, a system rather than an event. Research supported by NASA explores these ideas, examining both their feasibility and their potential impact. Private companies, including Blue Origin and SpaceX, contribute to related technologies, even if not directly pursuing space elevators. The idea of a space elevator may seem distant, but it reflects a broader question. How can access to space become more efficient, more sustainable, more integrated into long-term activity? Even if the exact concept remains theoretical, it shapes how engineers and scientists think about the future. It represents a vision of space travel that is quieter, more continuous, less dependent on explosive launches, and more like infrastructure. When we think about traveling deeper into space, one challenge becomes immediately clear: distance. The solar system is vast. Even the closest planets are far away, when measured in practical terms of travel time. Using traditional chemical rockets, missions to distant planets can take months or even years. For journeys beyond the solar system, the timescales become far longer, too long for current human missions. This is why scientists and engineers have explored alternative propulsion systems. One of the most promising ideas is nuclear propulsion. Unlike chemical rockets, which rely on burning fuel to produce thrust, nuclear propulsion uses energy released from nuclear reactions. This energy can be used in different ways. One approach is nuclear thermal propulsion. In this system, a nuclear reactor heats a propellant, such as hydrogen, to extremely high temperatures. The heated gas expands and is expelled through a nozzle, producing thrust. Because the energy density of nuclear reactions is much higher than chemical reactions, this system can achieve greater efficiency. This means higher speeds, shorter travel times. Another approach is nuclear electric propulsion. In this system, a nuclear reactor generates electricity. This electricity powers engines that accelerate particles to high speeds, producing a continuous but low level of thrust. While the thrust is small, it can be applied over long periods, gradually increasing velocity. This makes it suitable for long-duration missions. Nuclear propulsion offers several advantages. It can reduce travel time. It can carry heavier payloads. It can support missions that would otherwise be impractical. For example, a journey to Mars could become faster, more flexible, more sustainable. Research supported by NASA continues to explore these technologies. Engineers study reactor design, safety systems, and mission integration. The goal is to develop propulsion systems that are both powerful and reliable. Private companies like SpaceX are also part of the broader ecosystem of space exploration. While their current focus is on chemical propulsion, advancements in launch capabilities support the development of future technologies. Nuclear propulsion is not without challenges. It requires careful handling of radioactive materials. It involves complex engineering, and it must meet strict safety standards, but the potential benefits are significant. It represents a step toward faster, more capable exploration, a way to reduce the vast distances of space. Speed is one of the defining limitations of space exploration. Even with powerful rockets, travel times remain long. Reaching Mars can take many months. Reaching the outer planets can take years. For missions beyond the solar system, current technology is not sufficient. This has led to ongoing research into faster methods of travel. Some approaches focus on improving existing systems, more efficient engines, better trajectories, continuous thrust over long periods. Other approaches explore entirely new concepts. Ion propulsion is one example. It uses electric fields to accelerate charged particles, producing a steady, efficient thrust. While the force is small, it can operate for extended durations, gradually building up speed. Over time, this can result in very high velocities. Another concept involves solar sails, large reflective surfaces that capture the momentum of sunlight. Photons, though small, carry energy and momentum. When they strike a surface, they exert a tiny force. Over time, this force can accelerate a spacecraft without the need for fuel. This makes solar sails an interesting option for long-duration missions. More advanced ideas include propulsion systems based on theoretical physics. Concepts such as warp drives or space-time manipulation. These ideas explore the possibility of altering space itself to achieve faster than light travel. At present, these remain speculative. They are based on equations and models, not practical engineering. But they illustrate how far the imagination extends. Research supported by NASA examines both practical and theoretical approaches. Each step forward improves our understanding. Private companies such as SpaceX and Blue Origin contribute by advancing launch systems and spacecraft design. These improvements make it easier to test new technologies. Faster space travel is not only about speed, it is also about efficiency, reliability, sustainability. Reducing travel time reduces risk. It makes missions more feasible. It opens new possibilities. And as technology evolves, the limits of travel begin to shift. What once seemed distant becomes reachable. What once required years may one day take months or less. The journey through space becomes shorter, more practical, more integrated into long-term exploration. As space missions become more complex and travel farther from Earth, one challenge becomes increasingly important. Decision making. When a spacecraft is close to Earth, communication is relatively fast. Commands can be sent, data can be received, adjustments can be made in near real time. But as distance increases, communication delays grow. Signals take minutes to travel between Earth and Mars, even longer for more distant destinations. This delay changes how missions must be managed. Spacecraft cannot rely entirely on instructions from Earth. They must be able to operate independently. This is where artificial intelligence becomes important. AI systems can process data on board. They can analyze conditions. They can make decisions without waiting for human input. This does not replace human control. It complements it, providing flexibility and responsiveness. For example, a spacecraft exploring a distant planet may need to navigate terrain, avoid obstacles, select areas of interest. An AI system can assist in these tasks, analyzing images, identifying patterns, making adjustments in real time. This increases efficiency. It allows missions to accomplish more within limited time. AI is also used in monitoring systems, detecting anomalies, predicting failures, adjusting operations to maintain stability. In long-duration missions, this capability becomes essential because immediate human intervention is not always possible. Research supported by NASA continues to develop AI systems for space exploration. These systems are tested in simulations and in real missions, gradually becoming more capable. Private companies like SpaceX integrate automation into spacecraft operations, improving reliability, reducing the need for constant human oversight. AI also plays a role in data analysis. Space missions generate large amounts of information, images, measurements, signals. Processing this data requires advanced systems. AI can help identify patterns that might otherwise be missed, helping scientists interpret results more effectively. The role of AI in space is not dramatic. It is subtle, quiet, operating in the background, making adjustments, supporting decisions, ensuring stability. And as missions extend further into space, its importance will continue to grow. Traveling beyond Earth's immediate environment introduces a different scale of challenge, distance, time, isolation. Deep space is not simply far away. It is an environment with its own conditions. Radiation levels are higher. Temperatures vary widely. There is no immediate support from Earth. Every system must function reliably over long periods. Human missions into deep space require careful planning. Life support systems must provide air, water, and food. Radiation protection must be considered. Psychological factors also become important. Extended isolation, limited communication, the absence of familiar surroundings. All of these affect human experience. Deep space travel is not only a technical challenge, it is also a human one. Robotic missions have already explored distant regions. They have traveled to the outer planets. They have left the solar system. These missions provide valuable data. They show what is possible, but human missions require additional layers of support. Systems must be redundant, reliable, capable of functioning without immediate repair. Research supported by NASA examines these challenges, studying how humans adapt to space environments, developing technologies that support long-duration missions. Private companies such as SpaceX contribute to this effort by developing spacecraft capable of carrying humans beyond low Earth orbit. The concept of deep space travel extends beyond individual missions. It involves building a system, a network of capabilities, launch systems, spacecraft, habitats, support infrastructure. Each part must work together. Deep space is not reached in a single step. It is approached gradually through a series of missions, each building on the last, each extending reach slightly further. As this process continues, destinations that once seemed distant become more accessible. Mars, the outer planets, even interstellar space, though still far beyond current capability, becomes part of long-term thinking. Deep space travel is not fast. It is not simple, but it is continuous, a steady expansion of capability, a gradual movement outward. And in that movement, the boundaries of exploration continue to expand. Beyond the planets of our solar system lies a much larger region, interstellar space, a vast expanse between stars. It is not empty, but it is extremely sparse. Distances here are measured not in millions, but in trillions of kilometers, or in light years. The distance light travels in 1 year. Even the nearest star system is several light years away. At current speeds, reaching such distances would take tens of thousands of years. This makes interstellar travel one of the most challenging goals in space exploration. And yet, it is still considered, not because it is easy, but because it defines the limits of what might be possible. One approach to interstellar missions involves robotic probes, small spacecraft designed to travel long distances over extended periods. These probes do not require life support. They do not need to return. They can operate autonomously, sending data back over vast distances. Some concepts explore the use of light sails, thin reflective structures pushed by powerful lasers or sunlight. These sails could accelerate small spacecraft to high speeds, potentially reaching nearby star systems within decades. Such missions remain experimental, but they represent a shift in thinking, from slow, massive spacecraft to lightweight, high-speed probes. Other ideas involve advanced propulsion systems, nuclear fusion, antimatter engines, concepts that remain theoretical but are studied for their potential. Research supported by NASA explores these possibilities, examining both the physics and the engineering challenges. Private companies like SpaceX contribute indirectly by advancing technologies that improve launch capabilities and spacecraft design. Interstellar missions are not immediate. They are long-term. They require sustained development, incremental progress. Each step builds on previous knowledge. Each advancement reduces uncertainty. The journey to other stars may not happen quickly, but the groundwork is being laid, quietly, gradually. As space technology continues to develop, a broader question begins to emerge. What is the role of humanity in space? Is space exploration a series of missions, or is it the beginning of something larger? The idea of humans living beyond Earth has been explored in many ways. Space stations, lunar bases, settlements on Mars. Each concept represents a step toward a sustained presence beyond our planet. Living in space requires adaptation. Gravity is different. Radiation levels are higher. Resources must be managed carefully. Closed systems must recycle air, water, and materials. These challenges are significant, but they are not insurmountable. Research supported by NASA studies how humans adapt to these environments, developing technologies that support long-term habitation. Private companies such as SpaceX and Blue Origin are exploring ways to make space more accessible, developing launch systems, habitats, transportation concepts. The future of humanity in space is not defined by a single moment. It is a process, a gradual expansion, from Earth to orbit, from orbit to the moon, from the moon to Mars, and possibly beyond. This expansion is not only physical, it is also conceptual. It changes how we think about our place in the universe. Earth becomes one location among many, not the only environment. But the starting point, the idea of becoming a multiplanetary species, is often discussed. It reflects a long-term perspective, one that considers not only exploration, but continuity, sustainability, resilience. Space is not only a destination, it is an extension, a continuation of human activity beyond Earth. This does not happen all at once. It happens step by step, mission by mission, technology by technology. Each advancement builds on the previous one. Each success makes the next step more achievable. And in this gradual movement outward, something changes. Space becomes less distant, less abstract, more connected to everyday understanding. The future of humanity in space remains uncertain. There are challenges, technical, economic, environmental, but there is also progress, continuous, measured, and steady. Organizations like NASA continue to lead scientific exploration. Private companies such as SpaceX and Blue Origin expand access and capability. Together, these efforts shape a future in which space is not only explored, but inhabited quietly, gradually, and with increasing presence.